Honorable ladies and gentlemen, I'm an undergraduate student from Shunjie Liverpool University. I'm very glad to have the opportunity to attend the conference online. The title of today's report is the Mixed Reality-Based Teleoperation System for Prefabricated Building Assembly. Next, I will start from three parts: introduction, contribution, and the main content. To enable more accurate and faster assembly with low carbon emission, improving efficiency and precision. In recent years, with growing focus on sustainability, the construction industry is shifting to low carbon practice. Prefabricated construction, which produce components in factories for on-site assembly, emit 8% less greenhouse gas than traditional methods, and even more with green materials. However, its assembly has drawbacks. This paper proposed an MR-based teleoperation method for industrial robotic arms, combined with a relative organism. Our research proposed a mixed reality-enabled teleoperation system for industrial robotic arm to address the challenges for material assembly in prefabricated buildings, include safety risk, energy inefficiency, and operational inaccuracy. We use ORA and ARC based on RRMC to enhance robotic control performance. Then we test the feasibility and accuracy through a new aluminum profile experiment and precision testing. This method integrates mixed reality technology with advanced motion control organism to enhance robotic arm manipulation. It uses TCP/IP for communication between Unity and XM6. The system first adopts a resolve rate motion controller, then improves precision with the optimal resolve acceleration organism, and finally combines compliance control of adaptability. It aims to boost assembly accuracy and efficiency while keeping low carbon emission, aligning with sustainable building goals. The resolve rate motion controller is the closed-loop pulse controller for generating streamlined motion of the end effector in the robotic test space with the velocity level command. While direct position control is less effective and operates at low frequency, velocity control is more advantageous for high frequency and dynamic control. The optimal resolve acceleration ensures synchronization by optimizing joint velocity and acceleration under constraints. It's minimizing a cost function to achieve accuracy acceleration level control. Use resolve acceleration control. Task space acceleration commands are mapped to the joint space commotion, enabling dynamic robotic arm control. Since the kinematrix constraints are linear, ensuring real-time responsiveness of robotic arm motion. We dynamically adjust the compliance matrix to enhance the compliance of the robotic arm in different environments. We used the UFactory Lag 6 robot and MetaQuest 3 for the study. More technical detail, please refer to our paper. To test if a robotic arm can replace human labor in variance assembly test, we need to check its flexibility. When operating the robotic arm via the mixed reality remote control frameworks, we test whether it can assemble a component as flexibly as the traditional method. For this, a small experiment was designed. Use IMR device to control the robotic arm to pick up an aluminum profile from the workbench and then placed them on a shelf made by an aluminum profile. As shown in the figure, this project has completed the task. With demonstrated its effective remote control function, it can achieve the automation of the basic assembly operations and can realize intuitive human-machine interaction through direct detection of the hand position as well as flexible adaptability to simple construction tasks. To test the accuracy, the operator performs 3 distinct hand movement trajectories using MetaQuest 3 with motion data. Then, the teleoperation system captures hand trajectory data and controls the XARM6 robotic arm to replicate the human demonstrate trajectories. Then we choose 200 points each from both the operator's hand trajectory and the robotic arm path. Then we evaluate the control accuracy of the robotic arm by comparing the trajectory constant rate between human demonstrate and robotic execute path. Here's the result. This figure shows a robotic arm close tracking hand motion across in tests with trajectory overlap rate of 97%, 92%, 94%, and 96%, providing high control accuracy. Then let's move on to the conclusion. The MR-based robotic arm teleoperation system can efficiently complete simple assembly tasks for prefabricated buildings with intuitive operation and a trajectory coincidence rate of 92% to 97%. The optimization algorithm effectively smooths out noise, and the system has certain anti-interface ability and environmental adaptability, supporting remote low-carbon assembly. In the future, we will expand task complexity, improve accuracy, and integrate intelligent function to support sustainability building development. The recommendations focus on the implement the MR teleoperation system in high-risk or precision prefabrication scenarios. Adapt and optimize control for large robot arm handling complex assembly tasks. The integrate digital twin and BIM technologies. This work was supported by the HTLU AI University Research Center. Jiangsu Province Engineering Research Center of Data Science and Cognitive Computation at XGTLU, and the Suzhou Municipal Key Laboratory for Intelligent Visual Engineering. That's all for today's report. If you are interested in our research or have any questions that need answering, please feel free to contact us via email. Thanks for your attention.